Welcome, everyone. It's the 12th episode of Tomorrow's Medicine podcast. My name is Arseniy, and today I'm talking to Christopher Chapman. Dr. Chapman, please outline to us who you are and what you do.
Yeah, hi everyone. I'm Chris Chapman. I'm a lecturer in bioengineering at Queen Mary University of London. I do primarily bioelectronics and implanted devices research for the last 10, 15 years of my career. Right now, we're actually focusing on using bioelectronics for trying to record and detect cancer in the brain specifically. So pretty interesting.
So you're working more on biotechnology and bioengineering stuff, yes? Is it correct?
So yeah, it's bioengineering. It's really interdisciplinary. We do a lot of material science, electrical engineering, mechanical engineering. Bioengineering is kind of this kind of discipline.
And I feel it's important to note that I've seen your recent LinkedIn post that you actually started to hire PhD students and open your lab or something. Can you clarify this to my audience?
Yeah, so I started at Queen Mary almost 3 years ago now. When I started there, I began the continuous advanced recording for cancer lab. It was just myself and a couple of master's students when we began, and now we've been really fortunate to receive some funding for. I now have 3 PhD students in the lab and 1 postdoc working on that, and a research assistant working on some patient interaction. And we're hiring 3 other PhD students, so kind of expanding rapidly. It's a really cool area of research right now, kind of looking at the intersection between bioelectronics and cancer biology.
That sounds fascinating. I can't wait to dive into it, and I decided to structure our conversation into 3 parts. First, we'll talk about bioengineering in general. Maybe you'll explain some confusions that I and my audience have. And next, we'll proceed to bioelectronics and the actual work you do. And we'll finish with the future of medicine, tomorrow's medicine section. Does it seem right?
Great. Yeah, perfect.
That's perfect. And so the first question to you is the usual one that I ask. What sparked your interest in bioengineering? What were your path from the undergraduate studies to where you are today?
Yeah, it's a great question. I was actually studying mechanical engineering in undergrad back in the US. And initially, I'd actually wanted to be an architect. Funny enough, but I decided that I actually kind of wanted to build things a bit more with my own hands. So this kind of, I went into mechanical engineering just because it was very broad. I thought like I could get a job. That'd be quite cool. And so I did get a job and I really didn't like it. So I worked for a year at a major telecommunications company, and it just wasn't for me. I think I wanted some more fast-paced kind of research, things going on, a bit more blue sky, like exciting, creative problem solving than what was offered to me there. So I ended up adding biomedical engineering as a major because I just remembered liking biology, and I was like, okay, I think the human body is really the most interesting machine that there is, in my opinion, and so it's quite a cool mixture of you're learning the same engineering principles but just learning how to apply them to biology. And I think it was really new. I think I was one of the first cohorts to graduate my university in undergrad with a biomedical engineering degree. At the time, it was mostly people that were going into medicine, so it was a lot of in the States you do a medical degree before or you do the undergraduate degree before the medical degree.
I believe it's necessary to outline the difference between bioengineering and biomedical engineering. Could you speak up to that?
That's true. Yeah, it's something that is used interchangeably a lot. Biomedical engineering is usually really applied to medicine. So you're looking at engineering, so like things like prosthetic hips, actual like medical devices a bit more often. And then bioengineering is a little bit more broad. So this can be, even looking at, insect bite forces or things like, swarming of insects for drones or fungi or other parts of biology that you can still engineer. It could be genetic engineering. It could be synthetic biology. A lot of these kind of things. So I use the term a bit broadly. I like bioengineering because it's a bit more encompassing of it's more inclusive for engineering in general. Um, but typically, what I'm doing is biomedical engineering as far as my laboratory's research is concerned.
And I'm curious how this mechanical engineer mindset helped you.
Yeah, it's really good. I think mechanical engineering is very hands-on. I went to a university that was very applied, so I was learning how to weld. I was learning how to do all these things, and I think in my track towards where I am now, building medical devices, although they are smaller than maybe like a railroad car or something, this is still a very hands-on process. Still, a lot of the stimulators, like cochlear implants, these are actually made still by hand in the factories. So there's a lot of kind of manual, dexterous labor that goes into soldering the joints, actually insulating everything well. So I kind of kept that with me throughout PhD and in my postdocs, wanting to actually develop and design these medical devices.
And what's your current job consists of? Is it more of architecting some mechanical systems, or different, more kind of a basic ground biologic research?
So we've both. So now my job is really leading the lab. I mean, I don't do as much research
So
as I wish I
managing.
did.
Yeah.
Yeah, so I'm a bit
Okay.
more of a manager now. But I guess in terms of the vision that I have for the lab at the moment, I've kind of separated it out into a few different pillars of research, and one of them being really a more biological. Let's develop some models to understand, how this brain cancer is occurring and growing into healthy tissue. And the other pillar is really like, can we develop new sensor materials and then medical devices that we can then implant into the other model, finally into some in vivo models at some point.
My first episode on the show was with my friend Oscar. He's a person who's trying his best to delve into neurotech and brain-computer interfaces. He's extremely
Mm-hmm.
interested in it. And my question to you is, what is the gap that your lab tries to fill, tries to bridge in the field of brain-computer interfaces?
Yeah, so we're specifically looking at one instance of where you would use a brain-computer interface, and this is detecting cancer recurrence. So when you have brain cancer, surgical resection is really the best way. So you always want to try to remove as much of the tumor as possible, but unfortunately, you can't usually remove it all because unlike if you have it in your pancreas or liver, you can't do more surgical resection than you want to, right? So the surgeons are a bit limited because it's the brain. So oftentimes it's near some delicate parts of the brain. They would lose some sensory function or something. So what happens is over 90% of patients experience recurrence of brain cancer after surgical removal, if it's a high-grade glioma. And so there's really no way to detect that. We don't know. You just have to go in for routine scans every 3 to 6 months. And then that's all it is. You just try to catch it as soon as possible. So what we're trying to do with our kind of brain-computer interface is that actually, could we use this technology that's being developed for other things like, wheelchair control, prosthetic limb control? Can we actually use those signals to detect if the brain cancer is coming back and detect it early because we get continuous monitoring from these rays that we implant?
So, in other words, you're trying to find patterns in neuron signaling by using these brain interfaces to predict by these patterns whether the person has a recurrence of brain cancer.
Exactly. Yeah. So it's some really interesting work. I mean, if anybody online is interested, there's a whole field of cancer neuroscience that's started fairly recently, the last 10 or so years. And it's really, really interesting how brain cancer is actually integrating itself into the neural networks in the brain. Changes spiking patterns, changes impedance of the brain as well. So there's some different kind of hallmark biosignals that you can detect that really seem like at the moment it could be good for detecting onset of glioblastoma recurrence.
And can you add more details on how this brain implants can help us monitor, for example, or treat the glioblastoma, other tumors?
Yeah, so it's really like a time thing. So you want, like, the clinicians want as much time to treat as possible, because once the tumor is recurring, it's usually treatment resistant. Going back into a second operation is very difficult. So they want as much time to understand, like, okay, let's try to treat it as quickly as possible and get back on chemotherapy and these kind of things. And so now, obviously, with the scans where they have every 3 to 6 months, I mean, it could recur right after a scan, and you wouldn't know for another, half of a year, or unless you were showing other symptoms. So with this device, the idea is that you could know immediately. Like, you would basically have a green or red light, be like, hey, you should go get this checked out because we detected some aberrant activity on your tumor margin, and you should go just get a scan now. So it kind of, in talking to patients, it actually seems like it would alleviate a lot of kind of mental burden from them, because there's a lot of anxiety around the scans, and when they go in for scans, the wait time after the scans to see if anything is actually recurring. So not only is it great from a clinician point of view, but actually from a patient point of view, we're really hoping that it can help alleviate this scan anxiety that they have between essentially waiting to see if your tumor is regrown or not.
Is it feasible to predict the cancer growing before it even shows on MRI?
I think so. Obviously, this is a gamble that we're taking in our lab. I mean, we think very firmly that yes, we can. And this is aided by a lot of the other work that's going on in the brain-computer interface field, where we have this massive increase in resolution of electrode arrays that are being made. So what we're trying to do essentially is we're trying to harness a lot of these microfabrication techniques that are making really high density. So this means a lot of electrodes, per square centimeter. And we're trying to harness that technology and put it into the brain for these electrodes. So the idea is that if you can get down to a kind of a cellular level, so we're talking tens of micrometers electrode size, you could actually potentially sense kind of oncoming glioblastoma recurrence if you have some minute shifts in power of your local field potentials.
And what is the biggest challenge right now? Is it more hard mechanical challenge, or does this challenge kind of adhere to a soft nature of biological tissues? What is the problem that you're solving currently?
Yeah, so one of the biggest issues we have is that it would be really easy if we could do everything with metal. Obviously, metal is very conductive. There's a long-standing history of putting metal wires into the brain, deep brain stimulation, all the stereotactic EEGs that are used fairly commonly. I mean, these are approved techniques. But the problem for cancer is if you're implanting something at the tumor margin, you need to be able to do focused radiotherapy through it, because this is the part of the gold standard treatment that they have to receive. Obviously, we can't change gold standard treatment with our device. And so what the biggest challenge we're trying to do now is actually design the entire device without using metal. So we're trying to make a new polymer system. So literally a new material that we can use that's high conductivity. It's got a different form factor, so we can pattern all the traces and all the electronics with that, and then use everything just fully polymeric. So one other benefit of that is that if it's fully polymeric, it can be quite stretchable and quite flexible, which, again, as you mentioned, for scarring and things in the brain, this is very important. So we really want to make sure that there is no issue with that.
And I've seen this buzzword, conductive elastomers. So
Yes.
this is exactly this polymers that you're referring to. Is it correct?
Yeah, that's correct. So we're making conductive elastomers with a specific polymer. So it's PDOT, if anybody knows. So PDOT's probably the most widely used one. What we're doing is we're making nanowires out of it, and we're trying to actually change them chemically so that they're quite highly conductive, and align them into specific traces on the electronics. So I'm getting a bit specific maybe. but it's quite interesting. So a lot of what we're doing is actually polymer chemistry and material science in order to kind of actually tackle these bigger problems of, can we really design a device that can be implanted into the brain and then have radiotherapy go through it.
You addressed some limitations of using metal for detecting and for doing these electrodes. Can we just summarize into points what are the biggest challenges of keeping some device inside a human brain? Is it
Yeah,
corrosion?
so so it depends. It depends what you're trying to do. If you're stimulating, corrosion can be a big issue. Usually, this is why they make platinum iridium electrodes. They're much more corrosion resistant. So metals are great. I have no problem with metals. They're very highly conductive. Platinum is expensive, obviously. So if you're doing device prototyping, it's very challenging. But traditionally, the main, I guess, issue with metal electronics has been that they're not flexible, which causes when your brain moves, because your brain moves, even when I'm talking now, it's just sloshing back and forth. Basically, if you have a non-flexible device in the brain, your brain moves around the device and it creates this kind of constant agitation, constant inflammation of the brain, which leads to increased scarring, which then, as you have this kind of chronic scarring, you actually get neuronal death around the device. So the exact neurons you're trying to record, you end up not being able to record anymore because they've died. And so this is what's happened with many of the devices that have been used. You see like the Michigan, Utah arrays has happened with them. I think even Neuralink has had some issues with electrode dropout. So this is typically what we call it. So you lose signal at an electrode surface. So one of the main ways people are trying to get around that is by making softer and more flexible electronics. This can be done with metals, but typically metals are very stiff. So you need to design them in a way that is helping to make them softer.
That's a fascinating information. I've never actually thought about it that if you put something non-flexible, that it will damage the surrounding tissue. Uh, it's a simple but a novel idea, I'd like to say. And
Yeah, it's really almost like getting a splinter, right? If you get a piece of wood in your skin, your body tries to protect itself by pushing it out, encapsulating with scar tissue, everything. So the same is true in the brain. It's different cells, obviously, because it's the brain, but it's a very similar process.
one more buzzword I want to address before moving on to the bigger picture. What is electrical impedance tomography, or EIT? Could you explain to
Yeah,
us?
that's a great question. So I've done a lot of electrical impedance tomography. I was as a postdoc for a couple of years. I was looking at trying to record, basically localize specific activity in peripheral nerves. So what EIT does, so electrical impedance is basically how conductive something is, right? So if you have, I'm trying to think why. So tissue has a conductivity because it's salt, right? It has saline in it. But cells actually impede the flow of electrons through it. So when you have more cellularized tissue, it can be higher impedance, so lower conductivity. Or if you have fewer cells, it's typically higher conductivity and lower impedance. And so what this electrical impedance tomography does is it actually uses multiple electrodes around kind of a central point of interest typically. And what it'll do is it measures impedance across all the electrodes. And because kind of spatially the area in between these electrodes, and you have all these different measurements of impedance across, and you can guess about where the current field is going, you can actually reconstruct where the differences in impedance are, right? So it's kind of like that's the tomography bit. So you can actually get a more or less, 3D compare, depending on how big your slice is. We'll say 3D. It's maybe more like 2D, but reconstruction of changes in impedance over time in a system. So the best use case of EIT so far has been lungs. So if you put, excuse me, a bunch of electrodes around your abdomen, and you inflate your lungs, you breathe in, this changes massively the impedance because, this is just space that's dead space that has a very high impedance. So it's been used well for that. Well, what I've been trying to do, not so much anymore using tomography, but still looking at electrical impedance, is measure changes in tissue impedance over time. So some really interesting work has come out of UCL with the EIT lab, looking at, can you actually detect single nerve firing within a bundle of nerves from using EIT. So the idea is that it's non-invasive in the sense it doesn't have to be inside the nerve. It's still invasive because it's on the nerve. But you can technically try to tell, where is this one fascicle in the nerve running spatially, which is very difficult to do without something that's actually been implanted inside the nerve, like a Utah array or something.
Great.
If that makes sense. Yeah.
Yeah, it absolutely does. And while you were talking, this idea sparked to me that before this point in the show, we've talked about this brain interface as an input device. And do you have experience, or do you working on ways to actually make it also an output device to put some signals that will maybe cure cancer? I'm just guessing.
Yeah.
Have no specific knowledge about it. So yeah, what can you say about the output technology that we can put in
Yeah,
there?
so I've worked a decent amount on stimulating peripheral nerves and the brain. So obviously, it's just a question of charge injection. So you just have to basically apply a voltage, and you push around the ions and stimulate the ion channels to open. There's a lot of material specific issues with that. As far as for our device, there's some really interesting research not done by my lab, but other labs that has implicated. So tumor treating fields are kind of hot topic right now. There's actually a device now on the market called the Optune electrode arrays. So this is for glioblastoma using tumor treating fields with electrodes on the scalp. So like a traditional EEG cap, kind of, if that makes sense. And there's a decent amount of evidence that shows that using tumor treating fields, this is essentially, it's not my exact area of expertise, so I don't want to say anything wrong, but it's alternating current that's applied through the brain. And what it does is it kind of disrupts the spindle formation during cell division. And so in rapidly dividing cells like cancer, obviously this means that they're going to be have more stunted growth compared to other cells that aren't dividing as much in the brain, like neurons. So this has a lot of good applications, and it's seeing some clinical use at the moment. So that's really exciting. There's a couple other companies in the UK I know of. So QV Bioelectronics are making an implantable device that is going to be using tumor treating fields, as far as I understand. And then Coherence Neuro is another company that's making some devices for cancer treatment, brain cancer treatment using electrical stimulation. I don't think they're using tumor treating fields, but they are using something similar. And so there's a lot of evidence that you can really stimulate the brain and create this kind of treatment effect, actually. Obviously, you could do things like electroporation as well. There's some groups that have been using even ultrasound to open the blood-brain barrier to increase the uptake of chemotherapy that's administered systemically. It's quite interesting in general. I think it's not exactly where we're working in because we're trying to get down the monitoring side of it. But it's part of this bigger push, and I know we're going to talk about kind of future things in a minute, but I think in general, kind of this idea of closing the loop is something I've been talking about a lot for the last few years, where, it's great to be able to stimulate, but if you don't stimulate when you need to stimulate, it's not really worth much. So you need to be able to both monitor and then make a decision and then stimulate after that. So we're really working on one side of it only, but the whole thing is really joined together. I mean, you need to be able to monitor, make a decision, and then stimulate on the same device. So this is really where the complicated bit comes in, is really joining these technologies up together.
Wow. A personal robot that tricks your brain. Like I,
Yeah,
I imagine the system that like beep beep, you have a brain cancer, and
yeah, pretty much. Yeah,
yeah,
that's what we're
and you
trying to
talked
do.
only about, if I'm not mistaken, only about the electrical stimulation, but we also need to outline the chemical stimulation, like putting some kind of chemotherapy maybe, like inside the brain.
Yes.
Is it a
Yeah,
thing?
yes. Yeah, we so actually I was working at Imperial College for 5 years before Queen Mary, and have developed a it's essentially a local chemotherapy releasing device using electricity. So it's quite cool. So again, part of the problem with brain cancer is that you have the blood-brain barrier, and so most chemotherapy doesn't go in very well, and so they're pretty limited on the number of drugs that they can use. And so what we thought is like, hey, why don't we just cross the blood-brain barrier with an implanted device? It sounds great. I mean, it's what we were doing, implanted devices. And so there's one technique called convection enhanced delivery, which is essentially implanting a catheter and then running just literally chemotherapy into the brain itself using like a syringe pump. This works. It is a bit limited in some ways. You know, delivery time can be quite long because it's an enclosed volume, so it needs to be very slow transfer rate of the liquid drug cocktail. So what we're trying to do, and this research is still ongoing, which is really cool. I suggest you look into it in the laboratory of Riley Green um, at Imperial College. But so they're actually looking at basically, can we use electrophoresis to just directly transfer chemotherapy from an electrode into the brain? So we kind of encapsulated in the conductive elastomers a bunch of charged drugs, implant them, and then switch the voltage on, and it pushes everything out. So you get this kind of solid state transfer where there's no liquid carrier. So you're not limited at all by the volume of the brain. And so we like to coin it sort of a drug bomb because you can just release it all at once. Ideally, at some point, it'll be more pulsed because cancer doesn't respond very well to like a one-off kind of treatment. But there's definitely a lot of work going on in that field. It's really interesting. Um,
And speaking about brain, and you outlined for me just right now the thing you were researching and you were doing, and I'm curious how feasible, again, just doubling down on my previous one of my previous questions, how feasible is that will create some artificial cheap or maybe artificial kind of micro robot that will adhere to brain's natural environment. Because in the biological systems, we have this kind of a little weird, little interesting, little microenvironment inside the tissue.
mhm.
And to truly have a symbiosis of our biological system and a fabricated one, we need to, I believe we need some huge innovation in material science, like really huge one.
Definitely. No, there's a lot of work going into that. Well, I think we're still very far away from that. And I will say, I mean, before I say anything else, I think one of the biggest hurdles really is patient uptake for brain implants. People don't want brain surgery, which I think is totally reasonable. It's very scary, and we don't have a ton of patients lining up to get brain implants, right? Especially if it's something that's like not necessary. If it's just to connect them to the metaverse or whatever, I don't think that this is something that too many people would be interested in my experience. But there have been some really big advancements in things called living electronics. Not sure if you're familiar with it. It's not a
No,
field I'm
no.
working in, but it's a field that a few people I know have been working in. It's really interesting. So it's kind of using this idea that um, can we make the electrodes themselves also like kind of synthetic biological tissue? Um, So I think that's kind of where the field is going. I mean, we see the problem, right? That like we've been using the same interfacing technology. I mean, we've been planting essentially platinum wires with some larger connects on them for years, right? And it kind of works, but there's not been a huge advancement, in my opinion, in this field in the last years. So I think, as far as material science, the most interesting thing is probably this kind of idea of a living kind of synthetic electrode that it has cells in it, it has some hydrogels, and actually can almost directly become the human tissue, right? And still maintain some level of charge transfer back so we can record signals off of it. I'm actually working on an exciting project at the moment, funded by the Advanced Research and Innovations Agency at the UK. So it was a bit of a crazy idea, but we're trying to see if we can actually scaffold electronics directly onto the cell surface. So again, like I think these are the things that we need to start thinking about, is that how do we, it's not just engineering hardware, it's actually like how do we engineer the hardware into the cellular microenvironment, like you're saying. I think this is really the next big field of bioelectronics. And there's a lot of people doing research on conjugated polymer systems or conductive elastomers doing these kind of things. I think that's where hopefully the field is going to end up going.
And where do you perceive there is a current innovation center in the world? Is London a top place to do that kind of research for now?
London's a good place for sure. I think maybe, London, if you expand it to Cambridge, Oxford, is quite a good center for brain-computer interface and these kind of things in general, stimulation as well. Obviously, the US has been a powerhouse in this field for a very long time and continue to be so, for sure, at the moment. And Switzerland as well is quite a good bioelectronics center.
Are there many labs that are doing relatively comparable work that you do?
Yeah, exactly what I do, I don't know. I mean, so I definitely Professor Riley Green at Imperial College, because this is where I was working before. So I think you take a little bit of where you were everywhere you go, right? It's hard
For
to
sure.
break the mold completely. But there's definitely, I think we're all working, it's a fairly small group of people in the end. Like you end up knowing most of the people in the field. Like you go to conferences, oh, it's so great. You see everybody. I think we're all working on the same idea in the sense that like we see the problems with brain computer interfaces and implantable electronics in general. And we're all using different material systems, or we're all kind of using our different ideas on what the fabrication pipeline should be, maybe addressing things like, how do we get to high density, or, how do we get a certain material to higher density? Maybe we can't get as high density as the metals, but, these kind of things. So we're all doing really similar things, but, different disease states, obviously, and also different material systems, different fabrication pipelines. So it's a fairly collaborative environment, to be honest. I think like we've realized, I can only talk for the UK's, kind of neurotechnology field, but it's a very difficult thing interfacing with the brain and interfacing the peripheral nervous system. So it really, it's been nice to collaborate with people, and especially London makes that really easy because we have quite a few universities close by, obviously in London, and then Oxford and Cambridge as well. So
that's great that you're surrounded by such a tight community of researchers, and I believe that holds true for every major research that's on a cutting edge, that is innovating when not so many people are actually doing it. And yeah, it's absolutely great. And you mentioned fabrication. I want to ask you the question about scalability of this kind of fabrication, but before, let's go through what is percolation threshold and why is it important in fabrication and manufacturing?
So percolation threshold, I mean, as far as what I've worked on it with is, when you're making a composite material that's going to be conductive, you need to hit it. I like to think about it as sticks stacking on top of each other, right? So if you ever, maybe I'm old, but if you play the game Pick Up Sticks or whatever, so you throw a bunch of sticks on the floor, and you try to pick them up without disturbing the other one, right? So you have a bunch of interconnected pathways. And essentially, this is what's happening, right? If you make a material that has a conductive bit and it has a non-conductive bit, the electrons need somewhere to go. And so the percolation threshold is essentially some number. It'll depend on how conductive your filler is, that you need to reach in a conductive elastomer to be able to conduct electricity. And so we've done a lot of work with that on PDOT, PSS, or just PDOT in general. But even things like silver nanowires or other types of metal conducting bits, there will be a percolation threshold, because if they don't contact each other, you're not going to conduct electricity through the bulk material. So yeah, we do a lot with that. I mean, actually, I think some researchers have now gone away from using percolation threshold in typical like mixing to be more like, oh, can we actually just make the conductive bits first and then backfill with elastomer or insulative bit. And I think this may be a more holistic approach, because you don't need to, count on kind of a more random interaction of wires, or nanowires, or particles in the system to hopefully reach some percolation threshold. Because usually there's some mechanical detriment to adding more filler, right? So the other side of it is that obviously if you had 100% conductive material, your material is going to be less stretchable or less flexible or something like that. And so it's really a balance you're trying to hit to get the material properties you want, but also be conductive enough.
Moving to fabrication, how scalable is the production of such brain devices that preserve all the features that we've talked about? And what are the biggest companies right now on the market that help to accelerate this production of such brain interfaces?
Yeah, I mean, there's a lot of them. They're really big in the field. I mentioned a few that are big in specifically cancer bioelectronics. So Novocure, QV Bioelectronics, and Coherence. There's been a really big push. I don't know if you've heard of Synchron before. So
I've heard about it. Yes.
Yeah. So they're making a new type of brain interface that's actually kind of from a stent. So they're putting a stent into one of the major vessels in the brain. And so it's a really cool idea of like being minimally invasive. So I think they're really leading a lot of other companies that I couldn't list off all their names, but they're leading on that front of trying something different, right? I mean, because again, like getting something implanted into the brain, really scary. Getting a vascular stent implanted, way less scary. This isn't obviously non-invasive, but it's minimally invasive. So there's a big push in a lot of the companies to try things that are a bit more out of the box. I mean, obviously you have Medtronic, you have, all these big companies that are making more traditional, pacemaker lead IPG kind of things, or DBS electrode IPG, or implanted pulse generator. I think, yeah, I mean, Synchron's been really cool to see them come like surging in as far as like getting funding and pushing that technology forward. So I think we need a lot more people working at this kind of minimally invasive interface. It's very difficult. I mean, if brain computer interfaces are going to become something that a normal person would consider getting, that is someone that maybe isn't currently affected by a disease, it needs to be something very minimally invasive, even if it's like a pill or something that they can take, right? So there's a lot of science fiction surrounding it, obviously, but this is part of the job that I really love, is that you can think about like, oh, actually, maybe we could do something like that. That would be really, really interesting. It's like probably read it in a book somewhere, but it's you can try to make it real life.
And how much does it cost? How much does it cost to produce a top-level brain-computer interface and actually scale it?
A lot. At the moment, I don't have a number for you. I'm not actually in the entrepreneurial side of it too much. But basically, what costs a lot is usually not the actual fabrication. It's the patient trials. It's all these kind of things, right? The clinical trials are very expensive, very long to run. So this is really where the devices usually stagnate. So it's just, you just need a lot of money to get through it, basically. Even large animal studies, very expensive.
Is there a huge headhunt for people in academia? So are there these huge companies constantly looking for people and trying to get them out of their labs to join the corporation's labs?
Yeah, I mean, I think it's funny, right? Because once you kind of start a lab and you're a bit like, there, you're kind of solidified into what you want to look at. It's very difficult to move, I feel anyway. I mean, I'm like really happy looking in my little, corner of the world for this specific thing. I think what is usually what's happening more is that it's more of like at the PhD or post PhD or postdoc level that you have. It's been more challenging to get postdocs in general. I think there's fewer people trying to be postdocs because it's I was a postdoc for 7 years before I got my a permanent position, and so it's not a very grounded state when you are working on contracts, especially if you have a visa like I was. So I think we have more people not pursuing postdocs and actually trying to go into these companies, because that is one benefit. Is a lot of these larger companies doing this kind of hardcore brain computer interface do want people with PhDs, and neurotechnology or bioengineering, biomedical engineering, whatever you want to call it, is one of the major places that they're looking. So yeah, I mean, I haven't had any of my PhD students graduate yet, but we'll see. Hopefully, they keep their mind open.
Yeah, we'll see how many of them keep doing
Yeah,
this, and which ones will become Wall Street managers. I'm also
yeah,
always monitoring people going to finance after PhD. That's a regular path,
that's
and
true.
that's a great place to move to the final topic and speak about the future of medicine. What's your personal vision? Let's say horizon of 10 to 15 years. What will change and what do you want to change? The second part is even more important.
Yeah, I mean, I'm going to go a bit rogue on this because I've been really. So I've got a grant, maybe 6 months ago, and the grant is mostly looking at patient interaction and engagement with specifically glioblastoma patients, because this is what we're working on, and it's really changed. I think through interacting with patients, it's really changed my perspective on everything. I think as an engineer, because we're not clinicians. We don't really interact with patients very often, and it's a bit hard unless you know somebody personally that has this specific type of cancer. You wouldn't necessarily have their input, right? And I think really, actually, the biggest thing I'm pushing on right now in the field, and I'm maybe trying to be a voice for this, is this idea of patient co-creation of devices and engaging patients sooner in this kind of whole idea of I'm an engineer. I have an idea. I think I can cure the world of this problem, but like, let's actually talk to the patients because in the same way where like, we come from different fields, right? You and I. And so the questions you ask me wouldn't necessarily be the ones that I would expect from another bioengineer, which is really important because this makes me think in a way that actually, can bring some sanity into what you're trying to do, right? So I think we've been really pushing on setting up more kind of networks and more actual frameworks for patients to be involved in the co-creation of medical devices. So I mean, 10 to 15 years is a fairly short time frame as far as actual developments, I think. So what I would really like to see is just real establishments put in place to bring patients to the forefront of medical device design, research, and also in industry, although I know it's more complicated in industry. But specifically for the research time, I think it's really important that we are looking at problems that exist, essentially, because you can design devices to do things that, as an engineer, I think make sense, but maybe for the patients it doesn't make any sense. And so that's really what I'm pushing on in the field. I think the future is an inclusive future of everybody, basically like patients having a say for what they want, because we really need to understand it. Clinicians having a say what they actually need, and engineers all working together, because at the moment we are really siloed into our specific areas, and it can be very difficult. I mean, I've been lucky that I have some clinical collaborators that are very research focused, but clinicians don't have time. engineers don't have time. People don't talk as much as they should, and then you end up with devices, that don't work, or there's not a market for it once they actually launch. So I think we can save the field a lot of money. We can save the field a lot of embarrassment as well by not launching devices that don't work, because it's really a delicate area of the brain-computer interface. If you launch a device that doesn't work or has some complications to it, this is really damaging for the reputation of the whole field. We really are trying to avoid that. So I think that's been one of the lags that has happened in the field, is that everyone's really cautious about actually trying to make bioelectronic devices, for real patient implantation. So I think that's the way forward. I think we need to be more holistic with the way we're looking at the problems. I do think, obviously, there's been a lot of investment in neurotechnology. So I think that that's been really positive. And there's definitely been a push now, at least in the UK. I don't know about in the US and the rest of Europe, but the UK, there's been a push towards trying to market kind of, I'll say, quote unquote, wellness devices that are maybe doing some sort of, there's a few on the market now for direct transcranial stimulation that are obviously they're scientifically sound, but they're not delivering the same amount of kind of current you would deliver maybe in a medical setting, right? So they can be marketed as direct to consumer. So there's this idea that like maybe if you can just let the consumer decide if they want a medical device, it can increase access. Obviously, it only increases access in wealthy countries and to people who can afford it, which I don't necessarily agree with. But I do think the NHS healthcare systems in general have a lot of catching up to do as far as accepting and promoting these devices being used.
Let me paraphrase the main idea of your vision. And you want to see this kind of... Do you know what agile is? In computer science and management, it's really popular. No. It's agile is a management process when you have constant loops of development and you have a constant feedback from every stage of the circle.
Yeah, and, it sounds a lot like what I was saying.
And I got this analogy is that you want to see this quote unquote clinical engineers incorporated into the medical systems that will interact with the patients, and patients would be like, no, I don't like this orange iPhone. Give me like white brain transplant. It sounded to me it's an interesting idea. And the second part was about establishing kind of entities, preserving the reputation of the field, and getting investment. And on this, I can ask you, what would you do if someone gave you a huge grant? Like, what's the most pressing issues right now? If we can put like $300 million into it, what would you do?
Yeah, I mean, there's been a lot of talk in the UK about establishing, I don't know if do you know what Bell Labs was?
No.
So this is basically in the US at some point, it was kind of an established research organization that just funded science, essentially, right? It was like, we want you to do your science, and that's it, no questions asked. And there's been a lot of conversations around that. I think they're calling the Lovelace Project here, trying to establish these more like focused research organizations. And I think setting up something like this, using that huge investment and just being like, let's get everybody who works on, neurotechnology in the same building on a campus in the UK, doing that and doing the best research they can do and just funding that research. I think that's the way forward if we really want to see like a step change. Because obviously, anyone listening who's familiar with Bell Labs will know that they, a lot of the techniques that were used for like optical drives, all these things were developed by Bell Labs, not necessarily even for that. It's just that they had so much investment in the people that it was, they weren't bogged down by bureaucracy. They weren't bogged down by other things in the academic system that we have to deal with. And I think that is what I would do with that money. is establish something like that for neurotechnology.
Okay, and more practical vision of tomorrow's medicine, do you see the future where these implants could be easily dissolvable? So, for example, it done its job for curing, for preventing, for monitoring cancer, and like it somehow analyzes that it's on its margin of life, kind
Yeah,
of
yeah.
corrosion, and it just disappears. Not disappears, but dissolves into the brain medium. Is
Yeah,
it
there's
technically
people doing
possible?
research on that actually. I mean, it's a big field of research. I think it's possible. The biggest issue I see is honestly the batteries. So if you have like implantable batteries or implantable pulse generators, you need that. I feel like that's a little bit more complicated to dissolve than like, okay, you can dissolve a magnesium electrode or something. It'll be bioresorbable, or some bioresorbable polymers. They exist, and we know we can make electrodes out of it. They might not be as good as other ones, but like you said, if it can be a kind of set and forget situation, that really unlocks a lot of different avenues. I think, yeah, for me, the biggest issue would be the IPGs. What do you do with those? Are they also bioresorbable? I don't know how you would make that happen, or can you maybe if they're like in a good location to kind of surgically remove after the lifetime of the device, it might be acceptable to the patients. Again, I don't know. Usually going to the hospital is something we're trying to avoid. So
Let's finish with the question, not with a question, with an advice from you for younger people like me who maybe want to work in the field that you're working on, and what is the best path right now to get into the field of bioelectronics, into neural interfaces. Maybe you'll outline some labs, some universities, or general degree names that you need to get.
yeah, I mean, I don't know. So material science is great. I think probably I should have done a material science degree when I was in university because everything I'm doing is material science. You don't realize, I think, when you're a university student, how basically everything is a material, and so it's probably that's the most catch-all kind of degree you could get if you really want it. It's not necessarily engineering, so there's some challenges with that. But yeah, I think like obviously there's a lot now. Biomedical engineering degrees are fairly common. Like a lot of universities have them. I think I'm I'm the recruitment officer for the biomedical engineering degree at Queen Mary. So obviously I have a lot of stats, but I think like in general, you learn, it's a really interesting degree, right? Because you're learning like maybe less specifically some of the engineering concepts that you would learn in mechanical engineering or aerospace engineering, things like that, right? So maybe you won't learn thermo 3 and 4, you'll just learn 1 and 2, but you replace those with more general knowledge of things like biology, how the different systems in the body work. So brain obviously being one of them, maybe cardiovascular, pulmonary, all these different systems. But I know for our degree, I mean, you learn about it in terms of how an engineer would think about it. So I think it's really cool. Like it's a really fun degree, and I think it's really important for if you want to do biomedical engineering research in general, bioelectronics included. You need to approach it from a standpoint of, okay, I am an engineer. I want to do this thing. I know engineering principles, but the body is really complicated. And it's a lot more complicated than something that humans have made, generally speaking, because, we still don't understand how a lot of things are happening in the body. So having that knowledge and being able to combine them, I think is really cool. And it actually is a fairly employable degree on a lot of different levels. So, you are an engineer. Obviously, we want to keep doing research. This is typically the path we see as students go on for master's degrees in more specific fields like maybe neurotechnology. So if you did want to do bioelectronics, you might want to try to do something like that where you have a bachelor's degree in an engineering, maybe biomedical engineering, and then go on to a more specific master's degree. And then if you did want to do a PhD, obviously look at you know different universities that have kind of bigger bioelectronics fields. Actually, I think I'm one of the only, if not the only person doing bioelectronics research at Queen Mary. But we have obviously, like in the UK, there's quite a big presence in London and Oxford and Cambridge and Strathclyde and Glasgow as well. Quite a few people doing really interesting research there.
Thank you very much, Christopher. It was an absolutely nice conversation. I kind of outlined step by step the vision for brain-computer interfaces, and I feel my audience enjoyed it a lot and learned a lot. I'll definitely share this episode with my friends, and yeah, thank you very much.
Yeah, thank you very much. It's really nice to talk.
Everyone, you need what to do. Subscribe to my channel, like this episode, and share it with your relatives, friends, colleagues, and let's provide education to the masses. Bye-bye, everyone.